All right, hi everyone. My name is Alex Morehead, and I'll be presenting a work basically revolving around graph representation learning for structure quality assessment of protein complexes. And then I'll also be walking us through some results that we have from Cas15 for quality assessment of protein complexes. This is a joint work with my co-authors Sean Chen, myself, and Jian Liu, and we were advised by our PhD advisor, Dr. Jianling Chung, who's here today. So as I mentioned before, we'll be focusing on QA, and we'll be looking at it mainly from a graph representation perspective for protein structures and protein complex structures. So we'll start with a little bit of introduction to the problem, some motivation, then we'll dive into the development of our methods, how they work, how they're trained, their data, and so on, and then we'll walk through results and conclusions. So to start off, the first question on people's minds is, what is EMA? So EMA stands for estimation of model accuracy. Basically, if I have a predicted 3D structure, it could be a complex structure or a tertiary structure, but here we're interested in complex structures. How does that compare to a native structure that we have? So that's what EMA really is set out to measure. Why do we need it? It's useful if you have a protein structure prediction model because you might predict many different variations of a protein structure for a target, but you don't know which one is the most accurate. So in that case, you can use an EMA method trained separately or with the model itself to tell you which one is the most accurate model you predicted. We often call this a protein structure decoy compared to the native. So there's generally two types of EMA methods. There's multi-model methods and single model methods. So multi-model methods, the way they generally work is you might have a pool of structures and you use the similarity between the structures to kind of guide your estimate of how the individual structures, what their quality is. So it's kind of a consensus-based approach. Single model methods in some ways are more appealing because they don't require you to have a pool of predicted or decoy structures. Instead, you would just take that structure and predict a single value that tells you how good this thing is without having to reference any other structure. So it's a little bit more versatile that way. And we aim for single model QA here. So to start, when we're approaching this problem, we took a high-level overview and said, let's look at different ways you can represent a protein. We're going to go with a graph representation, but there's other ways you can represent proteins. So there's a 1D representation, which many other people have talked about today or alluded to. So for example, you take the amino acid sequence in a protein. You could describe the whole protein as a single vector, or you could take each of the amino acids in the protein and form that as a vector. So you could have many features associated with each amino acid residue. Say, for example, language model embeddings. You could also have a 2D graph representation, which is complementary to the 1D. So you could add some structural information like a contact map or distance map and treat these as edge features in a graph. So this would be a two-dimensional graph on the level of residues or atoms if you're describing the protein structure that way. And then finally, a 3D graph representation would be lifting this two-dimensional graph up into Euclidean space. So now you're actually directly modeling the 3D coordinates of the protein and dealing with those in a direct way. So in our approach, we mainly focus on a 2D data representation, and we'll explain some of the reasoning why. So our method we call DProQA. Some bullet points or some high-level overview for DProQA. It's a single model method, as I previously alluded to, for protein complex structure EMA. In particular, DProQA, it represents proteins as a two-dimensional k-nearest neighbors graph. So for example, you would take each residue, look at its 10 or 20 nearest neighbors. That would be what k is, and that's how you construct the edges of the graph. You say each residue is connected to its top n neighbors in distance and closest in distance. In particular, we also conduct multitask learning on protein structure graphs. So we'll get into some more specifics of what that looks like here, but we find that doing more than one task at once when you're training this model is beneficial for downstream performance. In developing DProQA, it makes use of a signature gated graph transformer, which we'll walk through. Basically, what separates our method from previous methods. The high-level overview is we have a kind of hybrid between a pure transformer-based model and a graph neural network model, kind of finding a happy balance between the two. We trained DProQA on a new dataset called MAF2, and we'll get into the details of that, and as well as the docking decoys dataset from the DocGround dataset. DProQA was also evaluated on this other dataset that we introduced called DBM55AF2, which is basically docking benchmark 5.5 with AlphaFold 2 predicted decoys. And then finally, we show the performance of our method in the EMA category for complexes at Cas15. So let's get into the multitask learning part of DProQA. So we have two different objectives, regression and classification. For the regression, we found it helpful to predict the DocQ score. So that's our main target for this work, but the classification also helps, as we'll see. So the DocQ score, as it's already been mentioned many times today, it's a very useful measure of the overall quality of a protein complex decoy. So it has generally 4 different intervals you can break it up into: incorrect, acceptable, medium quality, or high quality, and those values for DocQ score fall in these intervals. So we basically regress these values. When we take a protein structure graph as input, our model is going to predict the DocQ score. In addition, we also find it useful to predict the class probabilities for each of these assignments. So in other words, what's the probability that each protein structure decoy fits into one of these bins? So not only predicting the actual value, but the bins as well gives you some kind of uncertainty estimate on which bin it actually falls into. And then in terms of how we view the protein structures, so this is also key. So not only do we have a graph neural network or graph transformer that we use, how you encode it's also very important. So I'll highlight some of the key points. So we have one-hot encoding of the sequence of the protein complex as input. That's a categorical variable. We also have some secondary structure information or context and other geometric features. For example, the phi and psi angle, so we get some backbone encoding. So we not only have a residue level encoding of the protein structure, where we're looking at the carbon alpha atom, but we also have some backbone context. We also have a positional encoding based on the graph Laplacian that essentially gives us a notion of distance between nodes in the graph, besides just Euclidean distance. So it could be based on the node features themselves. Then for the edge features, so if we're connecting 2 carbon alpha atoms, that would be, for example, the carbon alpha distances, carbon betas, and so on. A particular note, we have interchain contact encodings. So we use a method called Glinter to essentially predict the contacts between protein chains. So if 2 residues are connected to each other and they're from different chains, that contact encoding will essentially be a 1, telling our model, oh, this is where the interface is. So that's useful encoding for protein complex QA, or at least we hypothesize. Another point of note is we have a permutation invariant chain encoding. This is also very useful. Basically tells you if 2 chains or if 2 residues are from the same chain or not. And it's essentially a generalization of AlphaFold multimers positional encoding. But we do that for a sparse graph setting here, so it's a little bit more general for graphs. So then in terms of our data sets, I mentioned before we have the MAF2 data set that we make publicly available in this work. It's all linked to our GitHub, and essentially this data set is relatively high quality in terms of the average DocQ score in this data set. So you'll see we actually broke it down into 2 sections, and this is more of a historical reason. So when we first were setting out to build this data set, we only had access to AlphaFold 2. Shortly after, AlphaFold multimer became available, but we decided why throw away the AlphaFold 2 structures that we had predicted for these decoy structures from the EV coupling and deep homo data sets. Let's actually combine the 2, and you'll see that in these statistics, there's relative strengths and weaknesses, as you might expect. So AlphaFold 2 tends to predict a lot more incorrect decoy structures, versus AlphaFold multimer essentially switches the curves to being much more skewed to the high quality and medium quality decoys. So overall, the average DocQ score is around 0.6 for this data set. It's relatively high quality. We also, as I mentioned before, we have the DocGround data set. This is actually on average much lower, so usually about 0.15. Don't have any slides for that here, but in general, that averages out the average DocQ to about 0.35. And then for our test data set, that averages out to about 0.32 DocQ. So this is essentially, once we train a method, this is a blind test data set that is dissimilar from our training data set based on sequence identity. So it's a way that we quickly iterate and cross-validate our methods to see how well they're doing, at least in terms of computational metrics before CASP. So on average, as you see, the quality of this, the decoys in this data set is on average pretty low. Yeah, and as already mentioned before, the data splits. So we have around 10,000 decoys for training, around 3,500 for validation. And we do 30% sequence identity filtering between the train and test splits to make sure that there's non-redundancy there. And we also removed targets that didn't contain any acceptable or higher quality decoys. That was also a quality assurance step here. In terms of how we evaluate these methods, so if we have a trained model, how do we actually tell how well it does? And the metrics are key, as we'll find out later in a results section. So we'll just step through a little bit carefully how we're going to interpret these results. So the ranking loss, that's the first key metric. So if we have our model predicted DocQ score, we can use that to essentially take a pool of protein complex decoys, and we can assign a DocQ score to each of those, and we use that to rank from best to worst decoys. And essentially, if we pick the top 10, for example, top 10 decoys, or actually just the top decoy in this particular case, we can measure its difference between the actual best decoy's DocQ score. So for example, if the best DocQ score, the best decoy had a DocQ score of 0.23, and our model selected best decoy, had a .q score of 0.24, then the ranking loss would be very low. So we want to minimize that. And then the top end hit rate, this basically is for if you have a ranking model, whether it's a neural network or not, just any ranking model at all, if you choose a top end range, and so you essentially do that ranking approach, you take all the protein complex structures in a pool, and then you rank them in terms of some quality measure. You take the top, say, for example, 10, how many of those decoys were actually in the acceptable range or higher quality categories for Capri. That's essentially how we're scoring these methods. So ranking loss and top end hit rate. So for example, if you had a method that had a value of 5/2 or /3/2, that'd mean that the method in the top 10, for example, of its decoys that were ranked, 5 of them were acceptable, 3 of them were medium or high quality, and 2 of them were high quality. So now let's actually talk about some of the method development here. So here's an overall view of the pipeline for dproQA. So it takes a protein complex structure as input and encodes it as a two-dimensional k-nearest neighbors graph with initial node and edge features, as we talked about before. Then we perform a node and edge embedding layer. So essentially, we take those initial features and embed them with some linear and nonlinearities. Then once we have this initial latent protein graph, we'll use our new gated graph transformer multiple times to update these node and edge embeddings. And then the final layer, we will not update the edge embeddings, but just predict new node embeddings, use some aggregation on those node embeddings to get a single representation or latent representation of the protein complex structure, and then train the last few layers of the model to regress the .q score as a scalar value, and then also the class probabilities for the Capri categories. So here's an overview of the actual gated graph transformer architecture itself. So in particular, note it starts from left to right. So on the left, we have h sub ij. Can we see that? No, we can't see the cursor. So h sub ij just means the neighbor of node I. So h sub I would be the node features for node I. Oh, awesome. Thank you. So for example, if we're looking at h sub j, this is the node features of the neighbor j. This is a neighboring node for node I. So generally, we look at this from the perspective of node I. So it has a neighbor j. This could be another residue. I is a residue, so it has features. Essentially, we'll do the normal attention computation between the two to get some kind of similarity measure between them. Then of note, we all have these node and edge gates. So I'll walk through this one by one. So we'll combine the information between node I and node j. Then we'll infuse information from the edge information we have already from between those two residues. So for example, possibly distances or things like that. We have that information that we can fuse in here. Then we have a gating procedure, which is a little bit new for this method. So essentially, we have a trainable part of the network that lets it actually choose what type of edge information to allow between the carbon alpha atoms or the residues. Similarly, we have another gating mechanism on the nodes themselves. So we call this a node gate up here. This also allows the network to define how much information it wants to let come through from h sub j, or in other words, the features h sub j. Then we essentially update the node and edge features as shown here on the right separately. And then the last layer will just predict this h sub I for the next layer. So that's essentially how the method works. So in particular, we have essentially a way of combining information from neighboring nodes. And then we also have these learnable node and edge gates, which we'll see what they do for this task later on. So let's look at some results. So in terms of our computational metrics, so this is before CAST, but this is just internal validation once we've trained these models. And we compare to several state-of-the-art methods for protein complex QA. So for example, we have Z-rank2, GOPE, GNN Dove as comparisons, and we have some ablation versions of the method as well. And I'll explain what those mean in a little bit. To start with, let's just look at the best column. This means if you actually knew all the native structures ahead of time, what's the best that you could possibly achieve for these categories that we're talking about. So if we look at the top end hit rank, which is what we're looking at here, what we're going to look at is for dproQA, we have that it selected 10 in the second category and 3rd in the third category, which basically means that it achieved the best results for the last two categories for what you can do across all of these targets here. And then it achieved 12 for the acceptable quality bin. So that means that there was a gap of about 3 decoys that missed in that range when it ranked all the decoys. And then we'll actually introduce it in the next slide, but just to do so here, dpro-QA GT just means if we took out the node and edge gates that I previously introduced, what kind of performance do we get? So we see a little bit of a drop in terms of the middle and last category. So in other words, the model is missing out on some medium and high quality decoys just without those features. Similarly, if it only has an edge gate here, which is what GTE stands for, we also lose out on some high quality decoys, and same story for node gates. Now, if we look at ranking loss, this is more of the, okay, let's take all the decoys we have access to, let's rank them, and then let's choose the best one and see what its DocQ score was and compare that to the best, actual best DocQ score you can get with a decoy. So in general, dpro-QA has the best average results on the DBM55 dataset. So essentially, we compare that to all the other methods. I thought was particularly interesting to note is if you don't have node or edge gates, in other words, the method can't distinguish information automatically. It can't like filter out, potential noise between the connections between residues. In other words, it can't decide that. Then you're going to see QA performance drastically reduce. It looks like in general, the edge gates are more important than the node gates, but both are complementary here. So I think that's pretty interesting. And then finally, for CAS15 results. So comparing dpro-QA, called multicom EGNN here, just under a different name, we compare it to all the single model methods in CAS15, and we rank third. So we had a TM score ranking loss of 0.2. And then finally, to wrap up with the results and wrap up the talk, we'll just highlight a specific example from CAS15 that we thought was particularly interesting. So for this target, H111, you'll notice that the distribution of TM scores for the decoys is pretty much skewed towards 0.15, so very, very bad. So there's a lot of ways that you can select the wrong decoy for this target, and very few that you can actually select the correct one, as you see over here. And we find that dpro-QA in CAS15 was actually able to select one of the best decoys possible. So the loss it had here for TM score was very, very low compared to all the other methods. So we thought that was an interesting example. And with that, I will conclude my talk. Thank you for your attention.
Hi, thank you for the talk. I wonder if your scoring function model can distinguish the case where, for instance, if the individual subunit of the complexes are modeled pretty good, but the interface might be crap or completely wrong. Can your scoring model tell that from the good interface model?
Yeah, great question. I think, so one way you could look at it, so it doesn't directly predict or like give you that kind of uncertainty. Like in other words, if it thinks that the contact you gave it was kind of incorrect or off, it doesn't tell you directly, but one way you might be able to do that is look at the class probabilities for the Capri categories. If it's like very evenly distributed between categories, for example, like it doesn't know which bin to put that decoy in, that might be one measure of, oh, maybe the interfaces are wrong. So in that case, you might try a different interface contact prediction method, feed those contacts into it and see if the probabilities change. That might be one way to approach it.
Hi, over here, and you're right, exactly, thank you. And how much is it affected your way of scoring by proteins that go folding upon binding? I mean, we know that like alpha multimer does that pretty well, but since you're like making a little bit like a turnaround from that, so how is it affected? Okay.
So to make sure I understood your question, you're saying because we're using training data generated by AlphaFold multimer, like how does that affect our results or the method itself? Is that what your question was?
My question is like AlphaFold multimer, it works very well, but when you have folding upon binding, like say you have a very flexible protein and it goes structure only when it binds to something else. So then it goes a little bit less good. It's really good, but it's less good. Mm-hmm. So how much is like these kind of interactions? Score?
Yeah, great question. I think in general, since at the end of the day, this is a machine learning model, it's going to be relatively limited by the training data. So if the training data has certain biases, I'm likely to believe that the model also will inherit some of those. So like you said, if alpha-fold multimer is failing to capture certain essences of flexible proteins, then the model may do poorly for those. One way to possibly circumvent that is using alternative methods that you know are a little bit better for those special cases on those protein targets. Add those to the training data, and maybe you have like a special held out test set that only contains like really flexible proteins, and see if that improves your downstream results. I think that's the best way to approach it for, at least for now, with this method.
Are there any more questions?
Thank you for the talk. I was just wondering, do you have any plan on adopting your work on the antigen or antibody complex? I think that might work. And if that happens, is there any limitations on your method?
Yeah, thanks for asking the question. So as you might have been able to tell, I didn't explicitly highlight it, but the method is pretty general. So notice that the featurization is specific to protein complexes, but in principle, you could featurize it with antibody-specific information. So maybe embeddings for CDR regions, for example, if that's of interest to you. So in general, the method should be readily adaptable. We also have, developments in progress where we're trying to build on top of this work for protein complex QA. So if you're interested, feel free to reach out to us. We can give you some ideas specifically for antibodies. But yeah, the method should be fairly general. I think the key thing will be if you need to rewire your graphs differently for antibodies. Like for example, it may not make sense to always connect all the 20 closest residues to a single residue. Maybe you need to have a more selective process based on like the CDR loops. But in terms of the featurization, that also be specific to antibodies as well, or probably be helpful.